Welcome to the HC Insider Podcast, a podcast dedicated to the commodities sector and the people within it. I'm your host, Paul Chapman. Today we're talking wave power, seemingly an unlimited source of renewable energy with some distinct benefits both in its prevalence, its proximity to human populations mainly situated on the coastlines, and also a more consistent and less intermittent source of renewable power. However, to date, it's remained far behind solar and wind. It's even remained far behind tidal. Challenges of a marine environment, complex and heavy systems, and therefore a high levelized cost of energy has impacted its growth. That all might be set to change. Our guest is Jan Skjoldhammer. Jan is the founder and CEO of Noviocean and an inventor who might be revolutionizing wave power and its role in energy transition. As always, you can really support the show by leaving us a positive review on the platform you're listening on, and I hope you enjoy the episode. Jan, welcome to the show.
Thank you very much, Paul.
So we are talking wave power, and this is quite a journey for us to go on to understand what it is, how it's differentiated from other sources of renewable power and its advantages and some of the challenges to date. Before we go too far, though, what is the difference? What do we mean by wave power versus, say, tidal power and the sort of associated group of renewables focusing on water?
Yes, there is a major difference. Tidal power is focusing on the tidal streams, the horizontal movement of water at the surface and also deeper down. That is caused by the moon and the sun and the high and low tides. So certain areas of the Earth is well suited for tidal power. Wave power is based on the horizontal and or vertical movement of the waves up and down, and the force they then exert on the something in the water. It can be a plate, it can be a buoy, it can be an air chamber. Many ways to take up that energy from the waves.
So it kind of feels at the moment that we hear all about solar, we hear all about wind, and periodically you sort of see something to do with tidal power or wave power in the news. And I think that's why I'm finding this so fascinating, because there's huge potential here, but as yet it feels like sort of the poor third cousin of those other two. Before we move into wave and some of its benefits over tidal, I think it'd be instructive for all of us to just understand kind of where tidal energy power production is at and roughly how that works.
I'm not a tidal expert, of course, others do that better, but basically tidals are functioning where you have some sort of channel where the water can flow in and out, because the tide goes up and down every 6 hours, so the water will flowing in. For instance, between Madagascar and Africa, there's a narrow, area there. So you have, lots of water flowing in there and out. Then you have stream. Same also in Nova Scotia, for instance, is there like an elliptical long island. And also, of course, several places in the UK and the West Coast where the channels are. So when you have this water flowing in and out, you have a horizontal stream of water. So we put the turbine down. The turbine has the axle also horizontally, with a prop, just like an aircraft standing against the water, flowing against it, and then it turns around and you have energy. So it's very simple, just like a prop on any boat or aircraft standing in the way of the water, and that water spins the turbine or the prop and the generator on the same axle, actually with the gearbox onto it to have a higher RPM. Very simple. But then again, it's underwater all the time, which has some challenges. Mechanics underwater must have a very strong anchoring. And it's just 10% of the market globally compared to wave power, because it's just these areas where they have that fast flow of water. If I remember correctly, they're looking for something from 2 to 4 meters per second of horizontal flow to be efficient. Some systems like Minesto, which have an underwater dragon going forth and back like in 8s, they can have somewhat lower speed, I know.
It's more developed than wave, power, right? There's been more efforts gone into this to date, and we'll come on to the reasons for that. Just in terms of, I mean, the fundamental limitations, I guess, as you mentioned, are there's only certain areas where there is strong tidal action versus where waves are much more prevalent, particularly in the northern and southern hemisphere outside the tropics. I assume it's probably not very good for fish going through a turbine in between Africa and Madagascar as well. Is there an environmental impact with tidal?
It's a good question. Actually, it's been shown that there is no problem. They go very slowly around. It's not like an aircraft prop. They go, I don't know what the RPM is exactly, but they go very slow. So the fish just swim around it. They can see it, so there's no problem. Of course, the wind power turbines, the tip speed is not far away from the sound of the speed of sound. So they have a larger challenge there. But for tidal, it seems to be very nice towards the environment. Same also with wave power, by the way. No problems seen around wave or tidal.
Tidal power versus wave power. I assume that obviously tidal power is only available in those places that have strong tides. How does it contrast to wave power and just in sort of the opportunity, the prevalence and so forth?
Yeah, the main aspect of wave power versus tidal is the timing, and also the global potential is 10 times larger for wave power than for tidal. And wave power is mainly strongest on the west coasts of the continents due to the rotation of the Earth and the anti-clockwise winds hitting the continents. Actually, then more on the northern and southern hemisphere, a bit less around the equator because of the lower winds there. The waves there are a bit longer and lower, but also have lots of energy. So fully potential, but it's more from, let's say in Europe, from Trondheim in Norway down to Gibraltar, even a bit more south to Morocco and Mauritania, but mainly that aspect. And then starts again with strong power from Namibia and South Africa. And in the US, it's on the north and on the southern part there on the continent. And then Indonesia and Japan and all those.
Yeah, so we're looking at a globe, sort of basically outside of the tropics. There's lots of potential for wave power. What gets people excited, you excited about wave power, is just the water density and its capacity to therefore generate power. Can you just help us understand a bit of the physics and why, if we could get wave power right, you've suddenly got an engine there, so to speak, that's actually got a lot more oomph behind it than say just wind alone?
Yes, I guess we all have been out in boats or been swimming, and we can feel the enormous forces, especially when there are high waves out there. So we have felt that or understood that, all of us. The reason is that water has a weight which is 800 times larger or higher than wind. So if compared to wind power, for instance, well, the wind power is in general perhaps blowing 30 times faster than the waves moving in general. But since the weight is 800 times higher of the water, higher density, and the force is so much larger, so for a much smaller unit, you can extract much more energy. That's why calculations state that you can extract at least more than 2 times energy from the same sea area as opposed to wind power offshore.
Okay, so I want to get into kind of what's been done to date and the different types of ways of trying to capture this global power that's available to us. But you've already mentioned one of the challenges, which of course it's not, waves aren't equally distributed across the earth, but there's a large portion of the northern and the southern hemisphere that this could be really powerful. But there's a lot of reasons why, talking generally, wave power has yet to be commercially developed and a real tool in our toolkit when we're facing decarbonization. One of those, of course, well, the first one obviously is we're talking a marine environment here.
I think the first patent came on wave power in 1797, quite some time ago, and I think the first deployment was in 1907 or something, like in France. Many have tried, many have failed, and there's basically 2 reasons. One is that they break down because of the forces in nature. And number 2 is that the cost is too high. And why is the cost so high? It's mainly because of the effectiveness of the system. If you have a lot of tons of complex material out in the sea and a low output, it costs too much per megawatt hour, basically.
Yeah, exactly. I mean, these are quite complex, heavy machinery with a lot of moving parts that have been putting out in the roughest seas. We've sort of, I guess, set the scene. What do these wave power generators look like? What are the various attempts that have been made over the last 100 years? Just give us some sense of kind of the mechanics and the engineering behind some of these efforts. I think that also, obviously, to put your product in context as well.
Yes, they can be divided in many different ways. We would like to divide them in two ways. There are the ones that extract energy from the particles in the water by the laws of Newton, and the other systems are the one extracting energy by the laws of Archimedes, by buoyancy, air in the water. So many have as a vertical plate, a flap that goes forth and back, either close to shore or out to sea, and other ones being a tenured that bends over the waves like that by the weight. Some other ones are also deeper down in the oceans or under the waves, perhaps 3-4 meters below. And many work then on the particles. Our calculations show that you need 30 times the area to extract the same energy as with buoyancy if you use this sort of extracting, this sort of way of extracting energy. So we will have come to the conclusion that you have to use buoyancy, air in the water, to have high efficiency of the unit, and then, of course, have a lower cost per megawatt hour. So the way some systems are, that typical, quite common one is the oscillating water column. You have an air chamber close to the water surface, and then the water goes up and down inside. So we have air pressure going with high pressure and then low pressure, and expensive, an air turbine. That's one system for instance, and that's based on the particles because you really have buoyancy. And then other ones just bending across the sea surface, and then you have overtopping devices where water flows over something and then fall down a meter or two perhaps. All these have very low efficiency as opposed to the amount of material in the water. And then when you go to the ones using buoyancy, most of them are round floats with a maximum diameter of about 10 meters. Why is that? Well, because if you're larger than 10 meters and the wavelength is 30 meters, you're cutting the waves. There's a limitation there. In our solution, we go rectangular because the wave is by itself kind of rectangular, like a long sausage. So if you have a shape which looks the same, you can extract more energy per unit. So that's a way of doing it without coming into closely on our system right now. But there are different ways of extracting energy. But we claim that locking air in the water while the wave is rising, then releasing it upwards is the way to extract a huge amount of energy per unit.
Yeah, and we will put links to this in the show notes as well, because a lot of this requires a bit of visualization, which we can't do on a podcast. But yeah, so you've got there's lots of different sort of engineering solutions to try and capture this, and there's some fundamental limitations, along with the mechanics of waves, and then also the maintenance, the deployment, the cost, etc. Just before we move on, roughly speaking, how much money, who are are there a lot of people looking at wave energy? And roughly speaking, where is that sort of levelized cost of energy at the moment when we talk about wave power?
Yes, many have tried, and the development costs are kind of heavy or high because, it's expensive to first construct something with all the simulations, then testing in wave tanks, for instance, and then afterwards out to sea in a scale model, and then afterwards full scale. So, some companies, the burn rate to have something full scale in the water is anything from 10 million up to perhaps 60 million so far, and then even more for the later testing. So it's an expensive journey there. The cost per megawatt hour is important. Solar and wind power started at more than, 60 cents per kilowatt hour many years ago. And then by learning rate, it's been going down. And now it's low to, solar is down to perhaps 5 cents. But of course, just giving power at daytime. And also wind power is down to something similar. Onshore, offshore, depending on the area size, is perhaps down to 10 cents at best. But the culprit is that it's irregular. It comes and goes. And then you need storage on top. And storage has the cost of perhaps 20 cents. But back to our cost then for wave energy, there are tables and there are calculations showing in general wave energy at this stage has a cost from about 35 to 60 cents per kilowatt hour, which is kind of high.
Quite high, but potentially coming down. And there's a magic to wave energy, which we're about to go into, and how it complements and the potential power that's there. Before we do that, you and I had this discussion offline, but all of this sort of begs the question, given we've got solar and we've got wind and we've got batteries to solve for intermittency, why are we bothering with wave power? What's the sort of the gap, the issue with the current setup in your mind that wave power might solve? But what's the challenges with the suite of renewables that we have right now?
This is a sweet point. Really important question. Nowadays, we have a kind of moderate percentage of renewable energy by wind and solar in the grids. And right now, they're struggling with regulating power to deliver energy to the grids, just managing to deliver what is needed. The plan is then to have a 20-fold increase in wind and solar by 2050. So if we are struggling right now, it will be much worse just in very few years, because the intermittency, there's no wind for 10 days a month basically, and no sun for 14 hours a day. Add those together, it's 40% of the hours of the month where there's no wind basically and no sun. That has to be covered somewhere. So you can say, well, we just add batteries. But right now, you might notice there's a scarcity of minerals, isn't there? It's difficult to get lithium and cobalt. And if you go into power, for instance, the whole of Europe with wind and solar, and then add batteries for 40% of the hours of the month, the requirement of batteries is enormous. It's calculations show it's just impossible to do that. And also, even if it was possible, the cost, for battery storage is something like 20 cents per kilowatt hour. And that's a cost for the storage. It doesn't produce something. So add together then batteries plus storage, perhaps you're up to 25 cents. And then it's, of course, batteries are also unsustainable in many ways, both by production, later on decommissioning. So what if I say there is an alternative to fossils or storage, and that's wave power, because it's off-phased. So we can do the same as storage, the same as fossils, when there's no wind or no sun, but then directly to the grid without any extra cost. That's very important to understand.
The HC Insider podcast is brought to you by HC Group, a retained search, intelligence and advisory firm focused solely on the global energy and commodity sector. With 6 locations across Asia, Europe and the Americas and over 50 consultants. To find out more, go to our website, hcgroup.global. There, you can also sign up for our HC Insider content for more interviews and white papers on relevant trends and talent impacts in the commodities world.
The other challenge, of course, with the current suite of renewables, at least in the, solar and onshore wind, is obviously the land use as well. And you look at Europe, there's, it's been inhabited and developed for a long time. There's not much land available, and what there is, you have the typical NIMBYism, not in my backyard arguments sprout up when large windmills appear, and and then politics gets involved and birds start getting killed and so on.
Yeah.
But I guess that's another challenge as well, which again, if we're talking wave power, these things are out of sight as well.
Correctly, and also most people live by the coastlines, also large cities are by the coastline. So if you have wind power up in the mountains or somewhere where there's little people living, what do you need? Transmission lines, long transmission lines, costly transmission lines, which no one wants to cross the yard either. But if you have wave power out to sea, then the cables can go more or less directly into these large cities with a much less cost. And then the difference between wind power and wave power is that no one wants to see these large windmills. They're going up more than 200 meters up in the air. So they're often out to sea 50 kilometers or more. You need a long cable, and you need to transport yourself out for 3 hours in a large boat out for maintenance. Well, wave power can be very close to shore, still have the waves. So wave power will normally be from 500 meters to 5 kilometers out. So the cable is shorter. You use 1/2 the sea area for the same output. The maintenance, the OPEX, is of course much easier because you can go out in a small boat much more often if you like. So there's many advantages by this. And then of course, not visible, hardly audible, and it doesn't kill any birds or animal life. So if you add this together, I won't talk down, of course, wind power is definitely important in the energy mix. I'm just saying that wave power seems to have a very important, part of this, a big piece of the puzzle in the future.
Yeah, because you have kind of those relatively, they're very important things. They're lower cost, it's close in, less square meters. Maintenance should be easier. You don't have at least so far in your test, you don't have the same environmental impact from a wildlife standpoint. The big thing though, as we sort of said, like the challenges with the current renewable setup is obviously intermittency, and then how do you maintain a base load that we don't have to have backup hydrocarbons, nuclear, or whatever it might be, to support that. It always, in other words, renewables always being an adjunct, to having to basically spend twice to get the same kilowatt hours. But anyway, so how does, and this is sort of the magic that I kind of want to convey, how does wave power solve for that intermittency, or how does it contribute to that? And maybe we can start with this idea about how waves are generated by wind.
Yes, the wind over time and distance creates waves. And as I mentioned before, when the wind dissipates, the wave remains for days. The importance here is how they all look differently, separately and combined. The reader or the listener can go to our homepage, the document tab, and you will see a visual graph over wave power and wind power outside Ireland for a couple of weeks. And you can see how they differ in percentage and how they combine. So basically this, wind power offshore has a base load of about 10 to 15%. That's the lowest they get to per month. Wave power in the same area has 30% because it's much more stable. So by itself, it is a better energy source for the grid than wind power. And then the beauty comes in combining them, because when the wind dissipates, the waves have been built up over days. Then the waves are at the best. And then normally, after some days, when the waves start to go down again, the wind magically comes up again because, daily and seasonal variations. So they kind of go hand in hand. It's beautiful to look at these graphs. So then, as I mentioned, 10 to 15% base load of wind, 30% base load of wave power, which is in itself very important. But if you combine them, you will see 40 to 50% base load. And why is that important? Well, it's important because that difference is with wind power, when there's down to 10%, it has to be then covered by something else. And today, what is that? Gas. Fossils, 90%. That's why the world is sinking in the water, because we're burning so much fossils just those days. Those days you're paying also 30 to 50 cents per kilowatt hour. What if we those days can supply energy directly to the grid without storage, without long transmission cables, not visible, not audible, and with also a low cost? moderately cost in the beginning. In our case, below 200 from the first 3 megawatt area. Subsidies will be around 250 euros per megawatt hour, 25 cents. And also the spot price is very often above 25 cents. So either we have spot price at today's range or subsidies, we're going to profit from the first 3 megawatt area. That meaning that it's actually a no-brainer with the right system out there, because we can do what is needed, help the climate and make a profit at the same time. And then, if I may say then, to our system, we have a learning curve. If you start at 200, when you're passing 100 megawatt in the water, you're down to a cost of about 10 cents per kilowatt hour, but you get paid the double. Why is this important? Well, I want to see our units out in the water in the thousands to mitigate the climate crisis. And how? By pure business. If the utility companies and investors and operators make 100% profit per megawatt hour, this will be the catalyst for large deployments for the best of the climate. That's why I do this. And the business will make the difference.
Yeah, because also 10 years ago, the European Union had incredible incentives subsidizing the development of these, the wind and solar that's in place. That ship has probably sailed somewhat when it comes to waves, no pun intended. Okay, so before we move on to your solution, how it tackles that base load and the arrays and so on, it just strikes me as excuse me for being slightly a natural skeptic, but the sort of the theory sounds excellent, right? You've got a much more consistent source of power intensity itself that's much greater, and you've got all these added benefits of, it's out of sight but close by. I guess I don't understand why sort of we haven't gone, why no one has done this yet, right? I mean, why isn't wave power an important part of the mix? Is it just simply because someone hasn't designed the right structure, or what is it that's you think in your mind the reticence around wave power?
It's an excellent question. I may have asked the same question. There are many factors, of course. I mentioned that some just don't survive the storms, which is one factor. The other one have the high cost. One factor, for instance, is that the wave movement upwards is very often 0.5 meter per second, very slow. But on a generator, you might need 1,000 RPM. So we're changing a very slow motion in the wave over to a high RPM on the generator. Of course, you can have lower RPM, then you need a very large generator like on wind power, a heavy one as well. So we need, if you have a gearbox, it's many cogwheels, you need lubrication out to sea, and it's heavy, of course, and complex. Or you can use hydraulic motors to speed up that thing, but that's also heavy and costly. And you can use different sort of accumulators, but all these are very heavy. Looking at my system, I had the float in my drawer since I was 25 years old. So the rectangular float has all this potential. When I decided to go down, to do this, I sat down for 1 year, and I had some requirements to myself. I said, if I'm going to do this all the way, I need to fulfill some requirements. That the system should be light, with few parts, well-proven parts, and durable parts, and cost-effective. So I sat down, and honestly, I didn't look at the other ones. I just wanted to have an open mind. And I looked at cogwheels. So this 1,000 RPM problem went to my trash can. Looked at hydraulic motors, too expensive, too heavy, and also complex, in the trash can. Looked at change and gear ratios in the trash can. Accumulators, the same thing. And I finally got to this conclusion of finding the hydraulic cylinder, proven for 200 years, combined with the hydropower plant, the turbine. I could have 5 check marks, all my requirements. That's when I was finally satisfied. It took me 1 year. Then I looked at all the other ones after that, and I found, it might sound perhaps a bit arrogant, but the ones I threw in my trash cans are my competition. They've been using all these systems for years, and it doesn't work. So the sweet spot is the rectangular float combined with the hydraulic cylinder, both very well proven, with the hydraulic power plant, A Pelton turbine spins on water, can take 1000 RPM easily, lasts for 40 years. So we have to be very strict when you select your systems, and many have gone swimming and got this, flash of a mind. Let's do it this way or this way. Perhaps also been reading some books from some famous authors and following their way. And there's more to it as well, but basically, many have been in the trap of going with the wrong systems for years, and that's why we haven't been successful. You have to have the set requirements and look for those. Then I did the simulations by third party. It cost me 75,000 by Wavik in Portugal to evaluate, am I right, am I wrong? Those numbers came back fantastic. Then I said, I'll go for this full time.
Yeah. So we're now going to take on the thorny task of trying to very simply describe, what we're actually talking about here. Because I do love the idea that, when you were 25 years old, you drew this, got a patent for it, put it in the top drawer and forgot about it, had a career in aviation, property development, and then have come back to it. And I think this idea that it has to be economical for it to work, and all these subsidies are temporary and rolling off to some extent. What we've got here, if I can you correct me, so you've obviously got something tethered to the sea floor, let's call it a long string, and at the top of that is a float that sits on top of the water, and that's capturing the rise and fall of the ocean, the wave action, using then this cylinder that's got a turbine in it at the top that's using hydraulic pressure to sort of build up the pressure inside and then release it, and that fires the turbine and off you go, right?
I think it's a good description. The float, you can see it also on the web page if you go there. It's rectangular. In the first edition, it's 38 meters long, times 8 meters wide, times 4 meters high. So when the wave is in the lowest in the wave trough, we lock it hydraulically to the seafloor by closing one valve up by the Pelton turbine. So it sits there. And then the water can rise up to 3 meters on the side. So we latch 600 cubic meters of air underwater and 600 tons of lifting force. When we have the pressure we need, it differs between the different wave heights. This is typical in a 3 to 4 meters wave. It will be perhaps half in a wave of 1.5 meters. But anyway, then we open the valve, and at this time we have the water-filled cylinder, compression in the lower end of the cylinder up to 80 bars could be 50 to 80 bars depending on where we go. And then the water streams upwards in the so-called penstock, same word as used in hydropower plants, upwards to the Pelton turbine, hits the water turbine with up to 2,000 liters per second, 2 tons per second, hitting that turbine with 300 kilometers per hour. Imagine taking a large van and smashing it into the brick wall at 200 kilometers every second. That's 6 megawatt of lifting power. Bang. On the same axle, you have a generator. So it's so simple. No cogwheels, no gearbox, same axle, spins a generator, creates up to 6 megawatt in the lifting phase. And when it sinks down, there's nothing. It just keeps on turning by a flywheel, let's say. And then comes the next wave. And in average, then we can produce, officially we have been saying 500 kilowatt for some time because we wanted to be careful. The latest simulations show that we can get probably 900 kilowatt in waves of 5 meters or higher. So it's
from
very
a single
powerful.
unit.
From every unit, yeah. So that's with the PV panels on top, that's 2.7 gigawatt hours per year.
And just so I understand that, because when I think of that, I mean, that's great, but it only produces power in these sort of one-off events, every wave form peak, right?
Yeah.
How do you overcome the sort of the micro intermittency of that?
It depends on the receiving grid. If you have, for instance, 10 floats together, they will basically even out each other because they will be at different position and hitting the different waves, especially if you have 20 or more. If you have a large grid, it can take that fluctuations. If you have a smaller grid, for instance, an island that is more dependent on having stable energy, you can use supercapacitors and lithium ions, for instance, to even out that energy. There are different sources. You can use certain flywheel system also, on shore if you like, or on board. So that's a question on the grid basically. because it is intermittent, our power. But the wave is lasting, for instance, from 5 to 14 seconds normally.
Yeah, and the key word here is arrays, right? So you're having lots of these floats that are essentially capturing that full wave action at all different points, so that it should even it out, if I understand correctly.
Definitely, just like wind power, you will have an array. But then remember my statement in the beginning of the program, you will get twice the output per sea area. And you talked about the scarcity of land coming up. There will be a scarcity also of sea area now, because so many want to use it for anything from algae growth and of course the fishery. You have the ship lanes. Now we have wind power out there. So if you can get more power per sea area, it's important. And also you can co-locate wind power and wave power. So we get double the output per sea area out there and then you have 50% the cost per deployment for the lease of the area. So that's also an option if the wind and waves are both at the good level in that area.
So where are you at in this journey, Noviocean's journey? So, well, can you describe where you're at? So I know you've done various levels of testing and so on. Like, kind of, what's the business to date? How much have you put in, and what's the next stage? And kind of where are we at with this, the projected levelized cost of energy?
We've been going through so-called phase 1, 2, and 3 now. 3 is the last one, which corresponds to TRL level 6. So we've been doing first the simulation I just mentioned there about third-party Wavik in Portugal. Then we have been doing test at KTH University for several years in a test rig there. We have the power takeoff with a hydraulic cylinder pumping the piston up and down, simulating the wave, and then been making adjustment to the whole thing. Then we've been to our first in a coast laboratory in Plymouth about 2.5 years ago, first time, a wave tank. It's like a large swimming pool that can make waves by paddles going forth and back up to 1 meter height. So we went there with a about 4.5 meter long float. We call it NO1. Tested for 2 weeks. The results came back very nicely. Then out to sea, outside Stockholm for 2 months. Also functioned, perfectly well. Of course, some small adjustment to be made. There's always, things to do on new design, but basically it works from day one. Then back in the test rig for a while, build a new float, a larger float. We call it the NO2. It's 5.5 meter long times 1 meter times 0.65 high. Lifts 1.5 tons. Then back to a tank in Nantes in France, larger tank. Tested for 2 weeks again. Very successful. And then out to sea outside Stockholm this spring for 3 months. The simulation you can see on the homepage and the presentations there. You can see pictures of that one as well as simulations showing the numbers. And now we're going into so-called TRL 7, which is the full-scale design. So now we're working with ship designers and consultants to design the full float system. Well, the float plus the power takeoff. So the float goes in the water in about 2 years from now. Most lights are outside Spain in a test site there. And then for 1 winter for testing for the winches, the whole systems on board. And then we plan to have the power takeoff, the machinery going in 1 year after. It's a way of de-risking it and also doing different things. So in 3 years we plan to be fully operational out there. And then producing, more than 500 kilowatt for sure. And you asked about the cost. To date. So far, yes. Well, thanks to my previous venture, I had some in my back pocket. So I've been chosen to, spend quite a bit of money myself. That's fine. I think it's worth it. And we got grants of about 3 million in total. We have about 2 million left on that one, and some loans as well. So still I have 100% of the company, but now we're looking for, start to look for partners and or investors. We're looking for about 9 million in private capital, which will take us all through all these phases, the design, construction, deployment, and 1 year of testing. And I say very often that given that we are out in the water, and we can produce 500 kilowatt or more, my phone will turn, the color will switch from black to glowing red, because then so many will see that these guys have made it with this power output, which no one else has done before, with a low weight construction, 150 tons construction. The power to rate ratio is exceptional in that case. And also the systems are very simple. So we think things will happen very much in 3 years, but there's an opening to come into our company now in some way.
I think that's fantastic. And again, I think this story has sort of captivated me. You know, lots of things seem to align when you look at wave power, and it's just not something you really hear about. So I'm excited to have you on. Just to go back to it, as we draw to a close, just to understand scale. Can you just help us get some sense of in let's say 10 years time, what sort of number of these units, what scale of array is going to produce what level of power for, you know, the country that's attached to it?
I have to go a little bit backwards. The politicians in the European Union now, they want to see 40 gigawatts of ocean energy installed by 2050. And that means if we just take 10% of that market, that means 8,000 of our units needed to satisfy that requirement. So tidal power will probably take a quite substantial portion of that 40 gigawatt, because they're slightly ahead of wave power in development. Once we get going, we have, of course, as mentioned, a larger, potential globally and also in Europe than they. But so we estimate 10% or better from that market. That's 8,000 units, and that's a sale of about 12 billion euros coming into our company in the next 25 years. But then, importantly, also the global market is 6 times larger. So there's quite some potential out there. And if you add this together, you say the numbers are kind of interesting. So I say 1/2 the sea area for the same output, 1/2 the weight of offshore floating wind, 1/2 the number of parts, and we start at 1/3 the cost of wind power and sun power. So if we are right, the potential is kind of hard to grasp.
Well, again, we'll put the link to Novi Ocean in the show notes. I'm sure people are going to be interested to go look, and you've got some fantastic presentations there that have animated exactly how this works much better than I can describe. But I find this, I think, fascinating, and I really do hope, obviously, that it takes off, and for all the reasons discussed, is a substantial part of our energy mix in the future. Thank you for listening. If you enjoyed this episode and want to support the show, please give us a positive review on Apple Podcasts or Spotify.
To find out more about HC Insider and HC Group, a search and advisory firm dedicated to the commodity markets, visit our website at www.hcgroup.global. There you can find out more about our services and our offices around the world. There you can also find more content, from interviews to insight pieces to more podcasts focused on the commodity value chains. Thanks again for listening.